up okay?
It's okay. Yeah, we can see.
Good. Okay. Okay. Yeah. Thank you. Thank you very much for the introduction, and thank you for the invitation to come and present this webinar today. Again, my name is Joe Davidson. I'm an assistant professor for robotics and mechanical engineering at Oregon State University. And the name of my research group is the Intelligent Machines and Materials Lab. We primarily work on manipulation and effector design and tactile sensing. And talk today is going to be about dexterous manipulation in orchards, or at least working towards dexterous manipulation in orchards. And just by background, OSU Robotics, we have a graduate program in robotics, and we have a graduate program in AI. And it covers kind of the full breadth of robotics. And so here's a picture of Graff Hall, where all of our research labs are. It's been a growing program over the last 5 to 10 years. We have about 20 faculty now, and anywhere approximately 80 master's and PhD students. And OSU itself is located in the city of Corvallis, which is up in the northwest corner of the United States. And the closest urban area to OSU is the city of Portland. And we're on the West Coast, and in the West Coast of the United States, they grow a lot of specialty crops. So that's fresh markets, fruits, and vegetables. And if you look at the headlines today, it's a tough time to be a farmer for a lot of reasons. And some of those reasons are increasing uncertainty about the future availability of agricultural workers, the challenges related to climate change. And it's not hard to go and find headlines today just talking these things that are making it hard to grow food, and these certainly aren't unique to the United States. In Oregon, for example, was a particularly bad year for cherry growers last year, and that's because for multiple reasons, the market essentially collapsed. And so for a lot of growers, they weren't able to pay workers to pick their fruits. They left it on the tree to spoil. And so that's certainly not a good news story. And so about 3 or 4 years ago, the federal government started the U.S. federal government started the National AI Research Institutes program. And the United States Department of Agriculture, the USDA, also funded 5 of its own institutes specifically devoted to AI and ag. And there are 5 of them, and each of them is a $20 million institute. And I'll briefly talk about all of these starting at the top and going clockwise. So the most recent one is called AI Climate, and that's led by the University of Minnesota. And they're working on climate smart ag and with applications in forestry. And then we have AI Farms. And the lead for AI Farms is the University of Illinois in Urbana-Champaign. And they have applications related to edge computing, sustainability, often working in commodity crops and livestock. There's IRA, which is led by Iowa State University. They work on digital twins, crop breeding, looking at commodity crops as well. APHIS is led by the University of California, Davis. And they work on supply chain, nutrition, and post-harvest. And then last but not least, we come to AgAid. And AgAid stands for the AI Institute for Transforming Workforce and Decision Support. And the lead institution for this institute is Washington State University. And we focus on specialty crops. So these are the various organizations that are part of AgAid. So it's led by Washington State. Oregon State is a large participant, also University of California, Virginia. And then we have partners that work on broadening participation, education programs, and outreach. And here you can see we're geographically distributed across the country. And what sets AgAid apart from the other 4 USDA AI institutes is its focus on specialty crops. And what's unique about specialty crops is they're very diverse. They employ a significant fraction of the U.S. agricultural worker workforce, and upwards of 97%. U.S., they're mostly irrigated high-value crops, and they're often perennial systems. And so within the institute, it works in different areas, and that includes water. So, the status quo today is suboptimal water allocation. How do we do better with that? We have farm operations and suboptimal management decisions. How do we respond to things like weather events, like severe crop damage from early frost or heat stress? And then we get to labor, and the status quo today is uncertain and variable profitability. And most of my time is use cases and projects related to the labor intelligence. Okay. So the crops that we've been working on so far are tree fruits, which is what I'll primarily talk about today, grapes, and the California team is working a lot with almonds and pistachios, and then berries. And then we're organized around what we call research thrusts. And the ag-inspired research thrust are water allocation intelligence, farm operations intelligence, and labor intelligence. There are also research thrusts looking at fundamental topics in AI. Those include modeling systems of knowns and unknowns, multi-scale decision support, and interactive AI workflows. And then we have activities around adoption and technology transfer, workforce development, education extension. Okay, and so I happen to, along with Manoj Karki at WSU, I happen to co-lead the labor intelligence thrust. So that's where I'm going to spend most of my time talking today. And the specific projects that I want to talk about are those applications or use cases that require physical work or physical interaction with the crop. And the projects that I'm going to talk about are robotic apple harvesting and robotic dormant season pruning, with at the end a few thoughts about future research directions and hopefully Q&A at the end. Okay, so I think this audience is probably well aware of some of the technical challenges of working in these very unstructured environments, but let me just go through a few of them. When it comes to visual perception, some of the challenges include, and these aren't unique to orchards. I'm going to talk about orchards today, but these also extend to other specialty crop environments. So the challenge is really the visual perception is we have complex scenes. And so this is a sweet cherry orchard during the dormant season. And as a human looking at an image of these trees in this orchard, it's very difficult to tell which branch belongs to which tree. Is this tree in the foreground? Is this branch in the foreground? Is this branch in the background? It's just hard to tell as a person looking at these images. We have occlusions, and so these are fruit that are occluded by vegetation and other fruit within the tree. Then we have challenges around decision making. So this is an expert human pruner, and as she does this, and she does this process very fast, she's counting buds, she's looking at bud distributions, and she's taking in that information as she decides which limbs and which what branches she wants to cut. Okay. And then we look at some of the challenges of doing physical manipulation in the crop. We have a lot of clustering and clutter. We also have crops where the mechanics of the environment can be very different. And so this is an apple that's very short stem that's sitting on a thick limb, and it looks stiff to a robot that's interacting with it. But then we can have apples that are on these long, thin branches that are almost like pendulums, and you have to pull this a long ways before you can pick it. And this is an environment that looks more compliant to the robot. Okay, and then of course, we have market acceptance criteria where the fruit can't be bruised or damaged. And finally, we just have the challenges with seasonal constraints. It's hard to get data on physical picks if you can only do it for a couple of weeks out of the year. And if you look at applications like pollination or blossom thinning, maybe you only get a couple of days out of the year to test and collect data. And so I'm fortunate to work with a lot of colleagues to do visual perception and the decision-making tasks, but sorry, they just renovated our offices and the lights aren't quite dialed in yet. But I'm going to talk a little bit more about these challenges at the bottom. Those are the things that I'm working most on today. Okay, so I'll start off with harvesting, and this is something that I started working on as a grad student at Washington State University. And so the first thing that we did was just study the mechanics of human hand picking. So we had a glove, we instrumented it with 4 sensors, and we installed inertial measurement units, and we picked thousands of apples. And we tried to understand a little bit more about the physics of what goes into human hand picking. And then we designed a robot, we designed an end effector to try and replicate these mechanics. This was under-actuated, passively compliant gripper. And really the picking approach was pretty much a blind look and move or look and pick. And a couple of things that I realized back then was one, we had very little sensory input after we did the initial detection and localization of the fruit in the tree. The robot would reach, but it didn't know what was going to happen after that. And then I was always a little bit, as a PhD student trying to get to the program, I was always a little bit constrained just by seasonality. If you only have one time a year where you have a week to go collect data, it's just hard to make progress within those constraints. Okay, so once we started at OSU, we actually started on a project with trying to incorporate tactile feedback during fruit picking. And so this was, give me one sec here. So this was, we made our own sensors, and we took inspiration from the tactile sensors that came out of Harvard about 10 years ago, and these are MEMS barometers encased in silicone. And we had another passively compliant gripper, and we embedded these in the fingertips. And then I'll go ahead and play this video. And it's a little bit hard to tell, not the greatest video here, but we're executing a pick with the robot. And then we have 4 pressure sensors on each finger. And then I'm showing here the force magnitude on the wrist, and here we have the motor encoders. And so we attempt to pick, the normal forces go up. And then of course, as you start to pick that force torque sensor on the wrist, you start to see this peak in the force signal. And then once the fruit's picked, the pressure declines and the force torque sensor, the signal on the wrist goes down as well. And so, and we did this during the pandemic. It worked okay, at least as a starting point. But an issue we had was with these devices and these grippers that have these spanning fingers. When you're doing manipulation in these very cluttered environments, there are always these unintended collisions. And so an example here is you have a finger that contacts a branch. I think here where there was some example where there's vegetation between the finger and the fruit, and then here was the finger contacted a branch. And so what we started working on several years ago was, one, to address the issue of seasonality and just how hard it is to collect data from the field, is to build what we call a physical twin or a proxy. So not a digital twin, but a physical twin. And this is what it looks like. But to the best of our ability, we used what we knew about the physics of fruit picking from our own prior work and what we could find in the literature to design this mechanism. And there are several springs up top here. There's another spring here. And then I'll actually just go ahead and play this video so you can see what it looks like. And then we have magnets throughout the device, and we reach a certain tensile force that's similar to where the stem pops from the tree, and we try to replicate that through magnets. And so this is work led by a PhD student named Alejo Lopez, and it's a collaboration with my colleague, Professor Cindy Graham. And so what we did is we used this proxy as a data collection platform. And so we executed lots and lots of picks. And then what we went and did is we went out to the field and we collected data with our gripper and the real tree on real fruit picks, and we compared the two. Okay. And so this is going out to the tree, and what we started off doing is we used UR5 as a data collection device. So we probed a couple spots on the fruit to try and understand its orientation, just using the kinematics of the robot as a measuring device. And we got upwards of 40 to 50 fruit. I can't remember exactly how many it was. And then we replicated these exact same picks on the proxy in the lab, and we compared them. And so here the yellow signal is the real data, the blue signal is the proxy data. And so here we're looking at things like the z-force and comparing z-forces between on the wrist force torque sensor between the real picks and the proxy picks, looking at motor effort and so on. And what we found was that a classifier, a very simple GRASS classifier for predicting whether a pick was going to be successful, trained solely on the proxy, performed just as well as one trained solely on the real world data. And then we did some ablation studies, and we found, at least for the sensors that we were using on this particular design, that motor torque and position were the most important channels for determining whether a pick was going to be successful or not. So again, a little bit of a preliminary study. And then what we transitioned for is kind of fundamentally rethinking about how we were going to design the gripper. And as I mentioned several slides ago, when you have these finger-based designs where there's this opening span as you approach the fruit, and we always have these challenges of how do you deal with clustered fruit? A lot of times fruit are touching one another, and maybe a finger contacts the adjacent fruit that you're not trying to pick. You get vegetation, leaves, soft vegetation between the fingers and the fruit. What happens when you contact a branch? And so this really motivated us to think a little bit more about suction cups. And what we have settled on, or at least in the current prototype, is we have an arrangement in kind of a pyramidal shape of 3 bellows-style suction cups. And we're trying to approach the fruit with as small a form factor as possible as we're reaching through the tree. And where we started off with was just characterizing what's the right vacuum. And here are some of the examples from the lab where we're looking at how would we necessarily set the angle of the suction cup? What's the right vacuum? Here you can see the vacuum as we're actually executing a pick on this test rig. And from that, what we could start to do is with these soft compliant bellow style suction cups, identify what's the optimal tilt angle and what's the offset. Because I haven't mentioned it before, but we also have an in-hand camera in the center of this current prototype as well. Okay. And so once we identified what's the right design for the arrangement of these suction cups, we use the proxy itself to characterize what's the robustness of this device to localization error. Because we know we're always going to have some localization error in the get fruit's position within the tree. There's going to be some offset. How much error is okay and still pick a fruit? And so we looked at changing the role of the gripper with respect to the proxy. And then we looked at changing the offset as well as you start to shift it left and right. And then we also looked at different arrangements of the suction cups themselves. So we would call this delta yaw, where you have one suction cup on top, and then nabla yaw, where you have two suction cups on top. And this is an example of one of the picks that we're executing on the proxy. And here you can see the vacuum channels in each of the suction cups during the sequence of the pick. And this dashed black line is the net force on the force torque sensor. And this is work that we're actually going to present at ICRA in Yokohama next week as well. Leia will be there to present this paper. Okay, so we use the suction cups just for that initial attachment to the fruit, but after that, you still have to execute this picking action. And there's a very specific way that professional pickers pick an apple to make sure it doesn't get bruised and then you retain the stem. And that picking action requires substantial loads applied to the fruit. And we showed and we found that suction cups by themselves weren't enough to execute this picking sequence. So what we have done is we've added essentially a second mode. So we have suction cups plus fingers. And the way these things work is we have these telescoping fingers that emerge from the device. And you can kind of see how this works on the video here on the right. And they're on a cam system where they sweep outward, such that maybe if we have clusters and neighbors, and we want to push those away with this outward sweeping trajectory. And then eventually it comes back in and we use some mechanical advantage to very strongly clamp to the fruit. And so we have this multimodal device where we have this initial attachment with suction cups, and the suction cups actually help center the fruit along the center line. And then we have these fingers that sweep out on this outward trajectory to clamp it, and then we execute whatever type of picking controller that we try. Okay. And so this was, we tested this in the field for the very first time in Prosser, Washington. It was last November. And so some good early stage results, but still a lot to do with this. Something else that we're doing with regards to harvesting is that not all apples and not all orchard systems behave the same. And so we are collaborating with Wageningen University and Research in the Netherlands, and we're looking at the control aspect. How should we tune picking actions based on the specific type of orchard system? And how many trellis wires are there? How do the trees grow? How do they train the trees to the trellis wires? And the cultivar, because maybe Gala behaves differently than Fuji, behaves differently than Honeycrisp. And when we're doing this, we're also instrumenting the tree itself. So we've developed these wireless inertial measurement units, and we install them on certain parts throughout the tree, and we collect inertial signals during a pick. And we're trying to understand in the future, is there a certain sequence that we should pick fruit such that we want to minimize vibrations of neighbors and drop fruit to the ground? And so this is the Wageningen gripper. It's a large suction cup. And here you can see one of the inertial measurement units installed on the tree. And it's heavily instrumented. They have an in-hand camera, again, a force torque sensor. And we're still in the process of analyzing the data that we collected at the end of the year. Okay. When we were doing these picks, we were also, for some of the data collection, we were doing, I guess I would call it force exploration. And so what you see up here on this little visualization up on the top left is we have probed every fruit from a set workspace of the robot. So we park the robot at a spot. It can only reach so many apples in its workspace. We probe the positions of all those apples. And then what this visualization is showing is every pink one is showing the fruit that gets picked next in the sequence. And these frames, these reference frames, are showing the locations of the IMUs that were installed during that pick as well. And then if I were to play this video here, So one of the controllers that we're using is actually doing some force exploration. So it is going to a set point of 5 newtons, go back, go to a set point of 10 newtons, go back, go to a set point of 15 newtons, and go back. And you can see up here, and what we have here is a plot. It's a force-based controller, right? It's a controller that uses purely force feedback. And so this is the pose of the fruit, just using the robot's kinematics. This is trying to different force thresholds. Fortunately, it looks like the video's getting skipped, but here was the first set point of 5 newtons. You can see here are the acceleration signals. There were 3 different accelerometers in these 3 different modules. And now it's going to the set point of 10 newtons. And then it'll go back. But you get the idea. It's going to go back and it's going to go to a set point of 15 newtons. And we're trying to see how does the tree respond throughout these different tick sequences. And this is work that was led by Miranda in collaboration with Mark. And Miranda is a PhD student here at OSU, and Mark is an undergrad. Okay, so I'll go ahead and transition a bit to talking about pruning. So harvesting is the #1 most labor-intensive application. Pruning is number 2. And there are certainly, so there are mechanized hedging systems where you can go through and do this bulk cutting of a tree canopy, but they don't allow for selective pruning of individual branches, which is really important in these modern orchard systems that we have in the Pacific Northwest for getting canopy shapes that maximize yields of premium quality fruit. Okay, so if we talk about the different functionalities that are required in a pruning robot, well, first you have to sense and model a tree. And as I mentioned before, the orchard environment is unstructured and cluttered. Then you have to go through the decision-making process. I showed a video before of an expert pruner as she was deciding which branches and limbs to cut. But we've done studies that show that there's substantial variability between even expert human pruners and the decisions they make. So that makes it even harder to encode these rules in an algorithm. You have to efficiently plan collision-free motion, but trees are complex kinematic structures, and no tree is the same as its neighbor. And then finally, you have to execute precise cuts to do this precision pruning, but of course, sensors are noisy and models always have some error. So there's a lot going on here. And we started off by making our lives as simple as possible, and that's starting with an orchard system with relatively simple pruning. And it's called the upright fruiting offshoot, or the UFO for short. And this is what it looks like. So we have this base trunk, and then there's this horizontal support or cordon. And then on these UFO trees, and this is a sweet cherry tree, they'll train, the growers and the workers will train these vertical leaders. And they're typically anywhere from 7 to 9 vertical leaders. And those are shown in blue. And the fruit grow very close to these vertical leaders. And off these vertical leaders, you'll have side limbs. And the pruning rule is to cut side limbs off the vertical leaders. And so we did some early work, and this is work that was led by Alex and my colleague Cindy. We did some early work on semantics-guided skeletonization of these UFO systems. And the interesting thing about UFO systems is you don't really need a global model of the tree in order to decide how to prune it. You just need to look for something that grows vertical, something horizontal coming off that vertical limb, and where those 2 things intersect, that's your pruning point. There's not a lot of decision making that goes into that process of determining where to cut. Okay. So I'll show a picture of our pruning robot. So we published this in RAM last September, I believe. And this is the integrated system in the field. So we have a UR5, so 6-degree of freedom arm that's mounted on the back of an electric vehicle. There's no autonomous mobility. There's a human that drives this gator, is what we call it. And there's a 7th degree of freedom, another meter-long actuator that slides this back in front of the tree. And we have some electric bypass pruners that have been hacked into the UR5 controller. And then we use an eye-in-hand configuration with a RealSense D4035 camera, so an RGB camera. And I'll talk a little bit more about these different tasks and the integrated pipeline here in a bit. But we start off with, we pre-plan a lawnmower scanning pattern where we go to a set of discrete waypoints. And in each of those waypoints, we look for a pruning point. Okay. And to identify a pruning point, we start by doing a semantic segmentation of the scene. And the way we do that is we utilize optical flow computed from two RGB images. And then once we have that semantic mask, we'll have one for the foreground tree, one for the cutter. We then feed the branch mask into an instance segmentation network. And so I know mask RCNN for computer vision folks is probably an older network, but that's what we adopted at the time. And then once we do the instance segmentation, we do some statistics to look for intersections between the classes that are side limbs and the classes that are leaders. And then from that intersection point, we call this the pruning point. Okay. And to do the foreground background segmentation, we use purely simulated data and optical flow, right? So we feed an optical flow image computed from two successive RGB images. We feed that through the pix-to-pix network, and it's trained in simulated data in a simulated environment. This is a picture or an image, whatever our Blender environment looked like. To actually do the cutting, we use feedback control that blends two different modes. And at first, we start with a visual feedback controller that was trained in reinforcement, so using reinforcement learning. And so this is an image of the training pipeline in Blender, and the robot is taking in a segmented view of the scene from its eye and hand camera. And so the input is a scene segmentation, and the output is a control loss. And so at the time, it was a very simple policy where it was for a constant velocity going in towards the plane of the tree, move up, down, or left, right. And really what the goal here was is to establish contact between the branch and the cutter. Because once we sense contact through the force torque sensor on the wrist, we switch over to a force-based controller. It's called an admittance controller. And the way the admittance controller works, it's a very straightforward hand-tuned controller. The goal is to use force feedback to guide the branch to the fulcrum of the cutter. So it takes in the wrench. The input is the wrench from the wrist, and the output is the velocity. And this is the goal here. This is the target. And this is the target you need. You need this configuration of the branch with respect to the cutter in order to maximize the likelihood of cut success. Okay. And so I'll actually go ahead and show I'll show two videos. I'll show one of this controller, and it'll be narrated in the lab environment. Then I'll show it acting in the field environment. Yeah. You can actually see it once you go. You can actually see, that transition point when it detects contact with the branch and it switches over to the admittance controller. You can kind of see it at the end wiggling around a little bit as it searches for that goal configuration. And this is the same behavior during the field trials in the field. So it's making a visual correction, text contact, and then it's using that force signal as feedback to try and get to this goal configuration. Looks like the video is getting hung up. Hopefully that's playing on your end. And then it comes. Okay, so we tested this in the field for the first time in winter of 2022. And here are a couple images. Again, this is the pruning rule for a UFO system is cut side branches off vertical leaders. And here are a couple of images of the robot pruning. I think I have another video here that'll show a cut. So a lot of work, but we still only cut, we only attempted 38 branches. So a very, very small data set. And we were able to cut just over 50%. So we cut 22 of 38 branches. And here you can see, the runtime, and of course you can read the paper if you want a little more details about how these reporting criteria are broken down. It's taking 35 seconds to execute a cut, and that's between using the visual controller, it's using the admittance controller, executing the cut, which is a very small percentage, and then coming back. And so, a good first step, but just still so many things that we need to work on in terms of improving throughput. We also make some assumptions that this is a relatively planar environment, and that's not necessarily true because sometimes you have branches that point towards the road. Okay. And so what we're working on now is I'm really interested in the idea of using dynamic models of the plant, so some kind of physics model to plan how you want to manipulate that plant. And the test case that we've started with, and this is work that Chelsea and Jocelyn are leading, is with blueberries. And so we're thinking through blueberry pruning. And so this was work that we did a little bit earlier, about a month or two ago. And this is our experimental setup on top of the robot. So there's a big linear actuator on top of a clear path husky that will raise this rig up and down. And then we have another linear actuator that will extend this probe in and out of the shrub. And then here, and it's a little bit hard to see in the image, we have a load cell. So we can take force measurements, and then we have an Intel RealSense RGBD camera. And before we did all these probing, and here you can see on the plant, we have these pieces of blue tape. And so those are our probe points. And before we actually did the physical probing, we also scanned these shrubs with an RGBD sensor. I think this was a Microsoft Azure sensor that we used. You can see where these IMU modules are installed on the shrub as well. Okay. And what we're interested in not now is the idea of not send to real, but real to send. That is, if you create a digital model, whatever that model looks like, and we haven't done it yet, we haven't done that part. How do you ensure that it's actually somewhat representative of how the plant would behave mechanically? And so we're taking in situ physics measurements of the plants. And so what we have analyzed to this point is the stiffness of these canes, for different branch thicknesses, different heights on the plant. And eventually we hope to get to the point where we can use this in situ experimental data to try and validate some type of digital model of the plant once we actually get to that point. Okay. So I'll go ahead and stop there. There's lots of people that have actually done the real work. I just get to talk about it, but I have a lot of great colleagues from faculty colleagues from OSU and WSU, and just very fortunate to work with a great group of grad students. And then we have really excellent grower collaborators in Oregon and Washington, and certainly need to acknowledge and thank the funding agencies that have sponsored this work, and that's the National Science Foundation, the USDA, and the Washington Tree Fruit Research Commission, which is an industry-sponsored commodity group. So with that, I'll go ahead and stop and hopefully take questions.